last class, we talked about how to do the free bar diagram. So basically we need to, of course, free bar diagram is you need to free the body from the boundary condition. You have the outline shape without boundary condition and have the coordinates, whatever that's convenient for your calculation, and put all the forces, external applied force, reaction force. Just want to emphasize here that reaction force is actually considered one of the external applied force, but a lot of times students may forget. So that's why I put reaction force here separately. But since reaction force is the force applied by the wall or by the ground or any external supporting structure to the structure itself, so external applied force should be considered as one of the externally applied force. The only thing different is that when I have a structure, when I say, okay, I have force applied on structure, I give you the magnitude of force, I give the direction of force. But for reaction force, as one of the external applied force, normally you don't know the reaction. Of course, if it's two force member, you know the direction. But most of the time, you don't know the direction, you don't know the magnitude. So that is also a difference of the reaction force and external applied force in general term. And of course, when we need to find the internal force at a certain point, we need to know, we need also put the internal force at the cut surface and also the weight body if necessary. So we also need to figure out for different types of reactions, what kind of reaction force it supports. General rule is that if it constrains the movement in certain direction, you should have the corresponding reaction force. So for example, if it constrained for this one, it's free to move in the X direction, but it's constrained to move, it cannot move in the Y direction. So it should provide reaction force in the Y direction. And for the pin joint, it constrained to move in X and Y. So that's why it should have reaction force in the X and Y. And a lot of time it's unknown. And for this clamped, let's say if this is kind of a mean situation, it constrained to the translation degree freedom in X and Y, and also it cannot rotate. So the reaction force should be the reaction force in X direction, reaction force in Y direction, and a reaction moment, bending moment. So this is the most commonly used three types of the boundary condition: roller support, pin joint, and clamped. And of course, this is the screenshot from the statics if you want a complete reaction situation, like reaction boundary condition and reaction force you can provide. And for the sign convention, for the reaction force, truly it doesn't matter. So let's say if you, by just checking the structure, you know the reaction force in this direction, you can just put in this direction directly, and you know the after calculation, okay, F minus AX equal to 0 and X equal to F is positive value. So okay, our first assumption is correct. But when I said it doesn't matter is that, let's say when you see a structure like this, and somehow you assume that by expansion, you assume the reaction force is in this direction, it's okay, because now you have F plus AX equal to 0, and then your AX equal to negative F. So it basically means that now the actual reaction force is in the opposite direction of your assumption at the very beginning. So in the end, you get the same direction. No matter your first inspection, you assume the direction by expectation is correct or wrong. It doesn't matter. And of course, for a complicated situation, if you have the transverse force, you have the distributed force, you have the actual force and couple applied at free end, you have no idea what is the reaction force direction. So you just put everything in the positive direction based on the coordinates. Again, because reaction force is one type of the external applied force, their sign follow the coordinates. So normally for the global coordinates, this is positive X, positive Y, and of course, this is positive rotation. And for the sign convention of internal force, this is, I think this part is like confused a lot of students in previous semester. So I want to make it very clear here. Tension compression, normally there's no confusion. I mean, we know that whenever it's tension, it should be positive. So if we define this is positive, so what happened is that on this surface, this is positive surface because it's facing the positive X direction. Now, this is a positive internal force, normal force. And this surface, when you cut through this point, now this surface is facing the negative x direction. So this green surface is negative surface. And now this is the positive internal force, positive internal normal force. And same thing, you guys learned from statics that if the bending is make the beam curve in this way, we consider this is a positive bending. So now when we cut through this point C, and now we have two surfaces, this is again positive surface because it faces in positive x direction. Now the internal bending moment, positive bending moment should be in this direction because we define this as a positive bending moment, positive bending. And on the negative surface, now this clockwise becomes the positive bending moment on the negative surface. And for the shear, our statics and mechanics materials textbook, majority of the textbook, they define that this is considered as a positive shear. So in this situation, let's say if we have C point in between, and we want to know the internal shear force on this at this point. So again, this is a positive surface. Downward is considered as positive shear force because this is considered as a positive shear. And on the negative surface, this green surface, on this negative surface, upward is considered as the positive shear force, positive internal shear force, because that is what happened when we have the positive shear. So I consider this is a very important part because it's not like erection force in the end, you get a correct direction for the coordinates. For the internal force, remember that you were required to have the bending force and shear force, bending moment and shear force diagram. You do need to know what is the positive bending moment, what is the positive shear force. All of those, when you were asked to draw the bending moment shear force diagram, it's about the internal force, and you need to have the correct sign. So this part becomes very important. And of course, for tension compression, it's very simple. You know that whenever there's tension, it's positive. Whenever there's compression, it should be negative. So this is a sign convention for external applied force, including reaction force, sign convention for internal force. And so basically we are done with the free bar diagram. The next step, of course, is free bar diagram, right? Sorry, equilibrium equation. So we will mostly focus on 2D situation. Most of the time we have the force in the x direction, 0, force in the y direction, the sum of force in the y direction, 0, and moment about a certain point is 0. So we consider is the equilibrium. And of course, as I said, this xy, it can be the global xy direction, which is left, right, or upward at y. It can also be a local xy coordinates, whichever is convenient for you to the calculation. So for example, if you have inclined structure, and most of the time we put the x direction as the x direction, and then perpendicular to the x direction become the y direction, if that's easier for you to calculate. And we do know that as a structure problem, the final answer should not depend on your coordinate system. I mean, the very determining structure will fail or not does not depend on what your coordinate system is. So no matter what coordinate system you use, you should get the same final answer if the process is correct. So does not need to be global XY coordinates. And of course, the moment about a certain point, this point can be any point you want to use. But most of the time, we want to find the point that can make your calculation simplified, which can eliminate most of the forces We talk about this one later, but the point is it's your decision which point you want to use. And of course, sometimes we can replace one of the force equilibrium equation as another moment equilibrium equation. So we take moment equilibrium equation about 2 points and have one force equilibrium equation. So basically, for this 2D problem, we can solve 3 unknown using 3 equations. And of course, sometimes if I have the redundant support, then it becomes static indeterminate. We'll talk about that one later, how to calculate static indeterminate system. But for a static determinate system, it's normally for 2D situation, is we can calculate 3 unknowns using 3 equations. These 3 equations can be force in the X, force in the Y, and a moment about a point. Or you can have replace this one or this one using the moment equilibrium equation, whatever makes it easier for you for the calculation. And a lot of time we also want to calculate the equilibrium at a joint. So basically, again, we consider the joint is a pin joint, so we have the force in the 2 dimension, Z0. Pin joint means there's no moment generated at the joint. One thing I want to emphasize here, since we are this is after we separate the body from the boundary coordination and everything, when we write this equilibrium equation, all the force should follow the coordinates for the calculation. So now, let's say if in the end we put this one, we want to calculate everything on this section at this C point, and we use this section for calculation. And when you put this into equation, this is you should put this as a negative sign and this as a positive sign, because now for this cut section, for this small section, all this force becomes external plane force, and everything should follow the coordinates. So this is the free body diagram, equilibrium equation, and the sign. How to determine sign for the reaction force, how to determine sign for the internal force, and what sign should we use when we write the equilibrium equation. So this is all the theory part. This should be covered in your statics in the previous semesters. So now let's check several example problems to help you understand the concept. The first one is the internal force at C. So C, I put it here and give dimension 3 and 6, and of course C can be anywhere in this beam. This is just one of the example. If you know how to calculate C point here, you know how to calculate C at any random point. So for this one, how do we calculate internal force at C? Any idea?
We first begin by determining the reaction forces at A.
Reaction force at A. And
the distributive load.
Distributive load. So basically, distributive of this section, right?
Yeah.
Yeah, okay. So yes, that is one way of calculating internal force at point C. So let's say when we need to calculate internal force at point C, we need to have cut structure through the point C. And of course, if we choose this side, the AC section, we can choose either the left side or the right side. If you choose the AC section, we do need to calculate reaction force at A. So basically it has reaction force X direction, Y direction, and a moment, right? We do need to calculate the 3, and then we have this section and do the free body diagram and the equilibrium equation of this AC section. We can calculate the internal force at point C. Another way is that, so basically we need to have 2 free body diagram equilibrium equation. First one is we do the free body diagram of the entire beam, the AB, and we calculate the reaction force here. And now we have, using the reaction force, we take the left side AC section and we calculate internal force. This is one method. The other method is that, as I said, we can also choose the right side. In this way, we do not need to calculate reaction force at point A because now it's all about the CB section. So for this CB section, you have the internal force on this side, of course. You have the distributive force. And you can use free body diagram equilibrium just use one section and it can be done. Make sense or not?
Sorry,
Both-
look, Brandon.
Sorry, what did you say? Do you have any question? Okay. So both methods should be fine. Both methods are correct, and you should get same answer in the end. You choose whatever you like. So in the class, let me use this side, and after class, you can try double check with this side to see if you can get the same answer. So let's say if we cut through point C and we choose this part. So for this distributive force here, of course, we know that there are internal force on this cutting surface. We figure out that one later. But for this distributive force, first we need to find the equivalent concentrated force. So what is the equivalent concentrated force for this part? How to calculate? How to calculate equivalent concentrated force?
Is
Could
it
you
the
use
length?
the area equation for
Yeah.
the triangle
Yes.
and then use the 270?
Yes. So basically, you need to find the equivalent concentrated force should be the area under this load line, right? So it's area of the triangle, and the equivalent concentrated force should be applied, pass through the centroid of the triangle. So you need to figure out where the centroid. So first for the area, how to calculate the area of this one?
1/2 times the base times the height.
Yes. So anyone can give me a number. What the area? What the equivalent concentrated force?
1,215. Well, for the whole thing, that's just the
Yeah, that's the thing I want to emphasize it. You need to be careful because we only take the CB section. So you need to figure out the equivalent concentrated force only for this part, not
would it be 810?
810. Why?
6 times 270 divided by 2.
So again, that's what I talked about. Be very careful. 6,
This is
270 is
so-
here. 270 is here. Right? You have 6 here, you have 270 here.
So how are we supposed to know
Would
the
it-
height? This
Would
triangle.
it be 720?
Sorry?
Would it be 720?
720. Why?
Should,
So the key thing here, we need to figure out the height here, the length here, right?
Don't you just use similar triangles? So like
Yes.
270 over 9 equals h over 6.
Yes,
And then you find like it's 180.
yes, 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 yes.
Mm.
So I feel like you guys all know the idea how to figure out, just in your calculation, you just need to be very careful how to find the equivalent concentrated force when we only consider CB section. So let's say we have the similar triangles, and I put this one as A prime, this one as C prime. So let's figure out the CC prime first. I think this some message in the chat. Okay. Yeah, it's 540. Thank you. So let's figure out let me show you the details of how to get the 540. So based on the similar triangles, we have CC prime, which is something we need to calculate. Of AA prime, which is 270 here, equal to 6/9, right? So CC prime becomes 180 Newton per meter. Now we calculate here is 180 Newton per meter. So the force is the area of this triangle. It's BCC prime. It's not the AA prime because we only consider the CB section. Let's put C prime here. So it becomes half of 180. I will put the unit here to show you that force in the end, it becomes Newton. So I have 6 meter and 540 Newton. So this is the equivalent concentrated force. Where should be this force applied? Where's the location?
Two meters from C.
Yes, thank you. The centroid of triangle. Again, this is the screenshot from the statics textbook. The centroid is 1/3 to this space. So here in our example problem is 2 meter to the C point. So the equivalent, let's say this is the equivalent concentrated force. It's applied here. Let's say this is the point D. CD should be equal to 2 meter.
I have a question. Does the Y centroid component matter here if we're just trying to find where exactly along the beam the force is acting, the equivalent one?
Have you heard about is a sliding vector or something like that in your static textbook? So the Y doesn't matter. It's about in the X direction. Because let's say, well, you can say that the centroid in the Y direction, you have this point and you apply it here, you apply it as long as it's a path through that line parallel, it should be fine. Because in the end, when you do the let's say force equilibrium in the X direction, the Y direction, no matter it's applied here or here, the equation should be the same. When you do the moment equilibrium equation, this is the force, this is the moment arm. The Y centroid, the Y location was centroid, when no matter it's here or you consider here or any point, it doesn't matter. It's still equal to the magnitude of the force times this moment arm. That's why it does not affect. We only need to write this CD equal to 2 meter. It's the location in the X direction. The Y direction doesn't matter. It does not affect our equilibrium equation calculation. Make sense or not?
Yes, thank you.
Welcome. Okay, so now we have the equivalent concentrated force. The next thing is calculate the internal force. So on this cutting surface, let's make it clear. Let's put it. So now let's assume that we have the equivalent concentrated force. This is 540 Newton and this is 2 meter. And on the cutting surface, based on our sign convention, back to the lecture note. Since we take the right side of the cutting point, so the cutting surface becomes a negative cutting surface. On the negative cutting surface, this is a positive normal force, this is a positive bending moment, this is a positive shear force. Make sure you put the correct sign there. So let's say on this cutting surface, we have the VC, MC, NC. Normal force, moment, bending moment, shear force. Based on the sign convention, this should be all positive on the negative cutting surface because this cutting surface is facing the negative x direction. So now writing the force equilibrium equation, Fx equals 0. And as I said, when we write the force equilibrium equation, everything in terms of cutting section, they become the external product force, and in terms of the entire structure, this is internal force. But now when we write the equilibrium equation of this cut section, now this becomes the external product force, or we can consider it's a force applied by this left section AC part to this to the CV part. So we need all the force in the equilibrium equation should follow the coordinates. So now we have, since there's nothing in the actual direction, and C equal to 0. This part is easy. Force in the y direction equal to 0. So we have VC upward, 540 downward. 540 Newton. Moment. Well, you can calculate moment about C point, about D point, about D point, whichever you prefer. But maybe about C point is easiest because now you can ignore this two. So moment about C equal to 0. Now we have the 540 will generate a clockwise moment. So clockwise should be a negative moment. Moment arm is 2 meters. And here we also have a clockwise moment on the cutting surface. Of course, we assume the global coordinates. This is a positive x. This is a positive y. This is the positive rotation. Shouldn't it be positive? Which one should be positive? Which one? MC? Is this equation correct? If this equation correct, then MC is a negative value, right? Why you believe it should be? Yeah. So in the moment equilibrium equation, since we in the global x, y, z coordinates, this is positive x, positive y, so the positive rotation is counterclockwise. So whenever you see a moment that is clockwise about that point you want to calculate, for example, when we calculate moment about point C, this one generates clockwise, so we should put negative sign here. And again, this one is also clockwise, negative. So this is the moment equilibrium equation, and we calculate a negative value. It means that the actual MC direction should be like this. Any question for this one? Any question for this example problem? If no, let's move on to the second example problem. Okay,
Wait,
back.
I'm sorry.
Yeah. Question?
For the moment, how did you calculate the internal moment, like the bending exactly again? I see that you did 2 times 540. Where did the 540 come from?
Here, equivalent force. We calculate the equivalent force of this distributed load becomes 540, right? So
Oh,
when
that's the distance from C, right?
yes.
Okay, I get it. Thank you.
Yeah, so for this one, we calculate equivalent concentrated force is 540, and we know that is it should be applied through the centroid of this area of this triangle. So the centroid is 1/3 to this C point. So we know that the CD equal 2. So when we calculate moment, it becomes force times moment arm. And since it's clockwise, negative sign. Any question?
Thank you.
You're welcome. Now of course, this is just a one simple example of how to deal with the linear change distributed force. Of course, I can change in this way, or I can change in this distributed force only applied on only section of the beam, not entire beam. You guys need to figure out like for the problem that derived from this one, how to calculate. The method should be the same as long as you understand. Any question for this one? Okay, let's move on to problem 2. So for this one, it's uniform distributed force, 1 kilonewton per meter. And we have dimension given. This dimension also given. Calculate internal force at point E. Two. Figure out later. So what should you do for calculating the internal force at point E? You can ignore this part for now because this is about like this just to show that it's double shear at this joint, at this pin joint. We talk about that double shear, single shear later. But for this only calculate internal force at point E, we can just ignore this one. So how to calculate internal force at point E?
Would you find the force that BD is exerting on A, and
Yes.
then use the distributed load and then find it from there?
Yes. How to find the force in BD?
You would break it up into its own full free body diagram?
Separate this part,
Yes. I
then
think.
how do you calculate? Well, you don't know the reaction force here. You don't know what the force applied by the
Oh,
rest,
okay.
right?
Mhm.
So how should we do?
Could you consider BD a two-force member to simplify it?
Yes, yes, yes. This is the key point that I use this one as example problem. Because I remember there was previous in the previous exam, there was one problem is involve the two force member, and a lot of students know that if it's a straight member, let's say I have a bar, it's a straight line. Everybody knows it's two force member. But when it's L shape, there were so many students confused. They didn't know that this one can also be a two force member. So for this one, instead of saying that reaction force is two unknowns, let's say dx, dy, and reaction unknown or dx, dy, they're independent to reaction force and become two unknowns. Here, since it's two force member, we know that the force direction should be in the BD direction, right? It becomes a two force member. So instead of saying that reaction force is a two unknowns, it becomes one unknown. So now for calculating reaction force, let's say separate the whole structure from the wall. Now we have three unknowns. We have three equations. This one is straight member, but it's not two force member because it has transfer force, it has force applied at B and the reaction force here. So this one is truly the AX, AY, two independent unknown. But here at D, since it's two force member for DB, it becomes one unknown. So now we have, if we do the free bar diagram and equilibrium equation for this entire structure, separate from the wall, we have three unknowns and we can have three equations. We can solve for all the reaction force. And for after solving the reaction force, well, cutting 3-point E, again, we can take either left side or we can take the right side. And of course, when we do the right side, we consider the BD force, we consider the force applied on top, right? Either side should be fine. You should get a correct answer. It just which one you consider is easier for you to calculate. So for the reaction force, let's first take the AC. So you can do the calculation of the entire structure separate from A boundary condition, D boundary condition, and do the calculation of this one. It's the same thing. And also the same thing if you do the free bar diagram of this horizontal beam, because the force applied at B, the direction is given. It's just the magnitude is unknown. So same thing, we can calculate, we have three unknowns and three equations. It's the same. So let's do it this way. Separate structure from point A, the pin joint, separate structure from point B. So now for the force, we know that at BD, it should have, this is the force, FBD. Magnitude unknown, direction is given. And we know the slope here based on the ratio of dimension. This is 4 meter, this is 3 meter. So let me put 4, 3 here. This indicates direction of the FBD. And for the reaction force at point A, as I said, it's not two force member, so we do need to have two unknowns. Reaction force in the X direction and reaction force in the Y direction. We just put everything in the positive X and positive Y direction, doesn't matter. If you get positive value, it means that is the same as our assumption. If it's get negative value, it means the opposite of our assumption. So for the complicated situation, we can just put everything in the positive first. Now for the free bar diagram. And equilibrium equation. Equilibrium equation of AC section. Where's the C? Okay, this is C point of AC section. First, if we take the moment about point B, we can calculate AY, right? Because now is the distributive force generate a counterclockwise, AY generate clockwise. We can calculate AY. So what is the equivalent concentrated force for the distributive force? Oh, you also use the calculated moment about point A. That's the same thing. You have the, because X component will not generate moment, the Y component of FBD will generate component. So in this way, you can calculate FBD in one equation, right? Either way, they're fine. So let's say for the point about B, we can calculate AY directly. What is the equivalent concentrated force for the distributive force?
Maybe 4 kilonewton.
94?
No, I said 4.
Oh, okay.
Isn't it 8 kilonewtons per meter?
Why?
Because you multiply the base times the height of the whole distributed force.
This is the one.
Oh, sorry, 6 kilonewtons.
Yes. So it's not 4. If you consider 4, you probably only consider like this part, but here we are taking the whole AC section. So we need to consider the equivalent concentrated force of the entire AC section, not just AB. Because if you only choose AB, I mean, how to deal with this CB part? You need to have another equivalent concentrated force and apply to this side. In the end, you get the same, but just make it unnecessarily complicated. The entire for the entire AC section, the equivalent concentrated force is equal to 1 kilonewton times 6 meters. And it should apply it at the center. So it should be 1 meter to the point B when we take a moment arm, take the moment about point B. So 6 is equivalent concentrated force. Moment arm should be 1 meter. And for the AY, it's clockwise. Distributive force will generate counterclockwise, so that's positive. And the moment arm, it's 4 meters. So this one equal to 0. AY equal to 1.5 kilonewton.
Wait, sorry, why is it 1 meter, not 2 meters?
Let me put it here. So this is 6, right? It should be at the center, at the middle point of AC section. Applied at the middle point of AC section. Make sense or not? Because it's uniform distributive force, it should be applied at the middle, in the center. And this middle point, 3 on this side, 3 on this side. So the CB, no, this is another point. That is E. Oh, no, it's not. A, B, C, D, E. Okay. Let's make a new point here. F point. Let's say this point should be 1. This distance should be 1 meter. This is the moment arm. This is the moment arm. Makes sense or not?
Yes, thank you.
Yeah. So force, moment arm, force, moment arm. AY equal to 1.5. Once we figure out AY, we can use force in the Y direction equal to 0 to calculate the BD. So AY minus 6 plus the y component becomes 3, 5, F, B, D. This is the y component of BD force. This one should be equal to 0. So we calculate BD force equal to 7.5 kilonewton. And then, of course, Fx equal to 0. We can calculate Ax. Ax. The x component of the FBD equal to 0. So Ax equal to -6. So this negative number means that the actual reaction force at point A in the x direction should be in the negative x direction, which makes sense because just imagine you have a structure like this and you have the distributive force applied downward. You should expect that without calculation, the pin joint should pull the whole structure in the negative x direction. So the calculation makes sense. So this is how we calculate reaction force at point A and the force in the BD. Any questions so far? And for the internal force at point E, and of course, you can use AE, you can use EC. Let's use AE. Either side is fine. Let's use AE. This is the E point. So we need to do the second step. We need to do a free body diagram and equilibrium equation of section AE. Reaction force, we already calculated the reaction force in the x direction is in the negative x direction and magnitude is 6 kilonewton. And in the y direction is upward 7.5. Oh no, 7.5 is BD, 1.5. And the internal force at point E, since this we take left side this time, now this cutting surface is facing the positive x, and so this is the positive x plane. And the positive x plane, for putting the internal force, we should follow this sign convention. This is the positive normal force, this is positive bending moment, this is positive internal shear force. So back here. Now, make sure that you put the positive shear force like this. So this is the VE. This is the normal force, NE. And this is the bending moment, ME. Again, force in the X, force in the Y, and a moment. We have force in X direction equal to 0. So NE minus 6 equal to 0. NE equal to 6. Second, force in Y equal to 0. We have (1.5) upward. We also have the equivalent concentrated force of this one. Be careful, don't get confused. AE equal to 2 meters. So the equivalent concentrated force should be 1 times 2. 1 kilonewton per meter times 2 meter. So this equivalent concentrated force applied on the AE section should be 1 times 2, downward, negative sign. And we also have VE. So VE equal to negative 0.5 kilonewton. Moment. You can do moment about A, you can do moment about E, doesn't matter. So let's say moment about E. Then we have this force pass through point E. So this moment arm 0. There's no moment contribution from this AX. This one will generate a clockwise moment. So, and the moment arm is 2 meter. So negative. So this three force 2 Newton, and moment arm center of the A section now it becomes 1 meter. Moment arm is 1 meter, and this will generate this equivalent concentrated force will generate a counterclockwise moment about point E, so it's positive. 2 times moment arm 1 and ME. So this is equal to 0. And of course, this one is moment about point E, so we can ignore these two forces. Now, moment. Bending moment at cross section equal to 1 kilonewton per meter. Sorry, times meter.
Sorry, to go back to the VE, if we assume that it was going downwards and our result became negative, that means there's a positive shear moment at that point E, right?
That's what I think I forgot what to say here. So good question. It's based on our sign convention of internal force. When we put the sign here for the internal force, we always need to put downward for the shear force as internal force on this cutting surface. But as I said, for writing the equilibrium equation, all the force should follow the coordinates. Does not depict the global coordinates, but you need to follow the coordinates. So let's say for this one, of course, with the global coordinates, then this one becomes a downward force when we write the equilibrium equation. This is the different sign convention for internal force. And when we actually do the equilibrium equation for this AE section, now this becomes the external applied force and everything should follow the coordinates. So if it's downward, you should add a negative sign. Counterclockwise, positive X direction, positive. When we do it in this way, we can make sure that when you have, let's say, as I said, you can either take this side or this side. And when we have this side for the calculation, free body diagonal equilibrium equation, and you put the shear force upward, you also get a positive value. In the end, we can make sure that you always get the same answer, no matter you take the left side or right side. For the AB section, if we did moment about point A, moment about point A, AB section, AB section. For the AB section.
I think the AC section.
Okay, AC section. So for the AC section, if we calculate moment about point A, let's calculate. I can show you. Where should I write? Let's move this one here. let's say if we want to write the moment about point A equal to 0 for the AC section, then of course this part is gone. This part is gone because, well, it's force applied at point A. It passed through the A. Moment arm 0. So we need to consider this concentrated force. This is 6. And this is the moment arm is 3 meters and it's clockwise. So it should be negative 6 times 3. And also we should have this FBD have X component, but X component pass through point A, the moment arm is 0. So this moment generated by the X component is 0. Moment generated by the Y component, this is a moment arm. So moment arm 4 meters, and the Y component we can write it as, and also it generates counterclockwise, so it's positive. This is the Y component, FBD. And moment arm is 4 equal to 0. You can calculate FBD.
I had a question.
Yes.
So you said if we had done for AE, if we had done the E, if we did EC instead and we did shear, will we also get negative despite the shear being upwards on the right side? I was confused on what you were trying to say there.
So yes, why we keep emphasizing that positive surface, negative surface, we need to put the we need to follow the sign convention. So it's because in the end, let's say if you have a tension and do the calculation, if you follow this sign convention, when you use the AC side, you will get a positive value when you put in this direction. And the same thing on the negative surface, you also get a positive value. It's in this direction, right? So this means that this internal force generate bending, and which makes sense because you should expect that if it cuts through this point and you have a tensile force applied, the force applied from the left side to the right, from the left side to right side should be pointing to this direction. And for if you consider this side, the left side, and the internal force should be in this direction. That's why we keep emphasizing that you need to put the correct sign. Now back to this equation, to this example problem. If we take the AE section, sorry, EC section, let's do it here. Copy. Now you need to, based on the sign convention here, you need to put the shear force upward, bending moment, ME, NE, no, this is VE, and this is positive, NE. And when you do the equilibrium equation, and you will see that you will get the same number and same sign, which should be like this because the bending moment, shear force, normal force for this internal force, no matter we take left side or we take the right side, you should have the same answer. If it's generated by tension, it should be positive no matter we take from the left side or right side. Right. So if we follow the sign convention of the internal force, so we put in this way, in the end, you can calculate after class, you will get the VE equal to negative 0.5. You will get moment positive 1. You will get normal force positive 6, which should make sense. It should be like that because the internal force inside of the structure should be the same no matter we do the calculation use the left side or right side. Let me use wait a second. Hmm. Let's stop the sharing. Probably can see, I don't know, it's too much to change back and forth. Can you see me? Using this one. So let's say if apply tension. So you should expect that if apply tension, the internal force at the cutting surface should be positive. So for this section, you should expect that internal force is in this direction is considered as general tension is in this direction, right? But on this side, cutting through the same point, when I choose this side, and now this is the cutting surface, for tension, it should generate the internal force should be in this direction. Make sense or not? So on different surface, cutting through the point on different surface, positive or negative surface, generated by tension, this one should point to this direction, and this one should point towards this direction. And for the shear, I define that when it's shear like this, is this considered positive shear in the statics and the mechanical material textbook? In the future class, it might be different. We'll talk about that later. But for these two classes, this is considered as positive shear, right? It's what I drew here. This is positive shear. So you should expect that again on this section, on this cutting surface, the positive shear force should be downward. But if I check this surface, for that shear force, positive shear force on this surface should be upward. Make sense or not? And the same thing for bending. We talk about that. This is very consistent in all the solid mechanics. With bending upward, consider as a positive bending. So again, we check this surface. This bending moment should again bending in this way. But on this surface, it's bending in this way for the positive bending moment. So that's why we want to make sure that you know, you always, when we put the internal force on the positive surface and negative surface, always follow the sign convention of the internal force. And when you do the calculation, we can make sure that no matter you use the left side or right side, you will get the same answer. You get the same sign, which should be the same, because for the internal force at a point, no matter you choose left side or right side, you should get the same answer. That's the same thing as in when you do the, I think there is one section in the statics asks you to calculate the internal force and drawing the bending moment diagram and shear force diagram. The bending moment and shear force should have its own sign convention, and when it's positive, when it's negative, should be fixed. It should not depend on you choose left side to the free body diagram or right side to the free body diagram.
Okay, and then I had a question about the moment about E, the last problem that we did.
Moment about E. Moment. Okay.
So you didn't factor in the moment about A for that. The moment about A ends up equaling 0, so it doesn't really matter. But for a different question, if there were a moment about A, would we have to factor that in when solving for a moment about E?
I'm a little confused. So when you calculate moment about E, it's all about what force can generate moment about E, right? When you calculate moment about A, then of course for this one you can solve the problem using moment about A. Then it becomes, well, these two you can just ignore it. This one will generate clockwise bending moment. This one is a counterclockwise bending moment. It's two separate equations.
Right. But let's say there was a moment about A of like 5 newtons per meter or 5 Newton meters or something, right? So would we have to factor that in when we're solving for the moment about E?
It's a pin joint, so there's no
Use reaction force.
moment.
Oh, okay.
Yeah, so okay, thank you. I guess I didn't understand the question. So basically, back to the boundary condition, what kind of reaction force can supply? If the pin joint is only, because pin joint is free to rotate, so there's no reaction moment. If it's clamped, then there's a reaction moment. So for the problem here, it's very clear that you can see here the pin joint is free to rotate at this point, and it's free rotate to at point D. So for all this boundary condition here, it does not have reaction moment. It only constrain the displacement in X, Y, and only have reaction force in the X and Y. It does not constrain the rotation and does not have reaction moment.
Thank you.
You're welcome.
Oh, sorry, one more thing. So to clarify, at point E, we would have a negative shear force based on what our answer was determined, right?
Yes, it's a negative. Yes.
Right.
Yes. So this positive negative sign, you can go back and check your static textbook. We do need to have very clear sign for the internal shear force and internal bending moment. If you remember, you were asked to draw the shear force and bending moment diagram. Both X force is positive. Why intention do we say, for example, both X force are positive? Because we calculate this on the convention as are you talking about this one?
I think he means that like when tension is pulling each side, how come both are positive despite one being in the negative direction always?
Do we agree that no matter like statics or mechanics material or any solid mechanics class, we always consider tensile as positive, compressive as negative, right? So if we agree that tensile is always positive, compressive is always negative. So let's say now we know this is positive. And if this is positive and we want to know the internal force of any random point in this structure, and we cut through that point. Now, for this cutting section, for this section of the left side, AC part, this should be the internal force at point C. And for the CB section, this should be the internal force at point C on the negative surface. This is how we generate tensile in the 1D bar. Makes sense or not? Any other question?
Yeah, since AY is in the positive direction, how come when we calculate the moment about E, we assume it to be negative?
AY.
Like we use negative 1.5 for the moment about E, but AY is positive.
AY is positive. Yes, AY is positive. How come? Where? This is positive.
At the bottom though, when we calculate the moment
This is
about
the
E.
moment. This is the moment. Moment is
Oh.
yeah. Is always counterclockwise. You put a positive sign. Clockwise, you put a negative sign because global coordinates. This is X. This is the Y, and this is the positive rotation. This is the sign for the moment. It's not a sign for the Y direction. Makes sense,
Oh,
no?
okay. Yeah. Thanks.
Yeah. Any other question? Any other question? I don't think we have time to do the third one. I will do the third one next class because we only have 4 minutes left. Any question about these two examples?
I have a question just about notation.
Okay.
I know you use like N and V. Like, let's just say that was point E. Can I say the internal forces are like EX and EY, or do I have to use like N or like NE and VE?
It really doesn't matter.
Oh, okay.
Yeah, you can use whatever you want, but I intentionally use N because N represent the normal force, and I use N. Some textbooks they're very consistent use N as the normal force and use V as shear force. Most textbooks we use in this way. Of course, you can use X and Y. It really doesn't matter. You can use. I just try to be consistent with textbook. Any other question? Okay, so if no questions, since we don't have enough time to solve the third example problem, I will do it in the next class. Thank you for coming and have a great day.
Do we have any homework or?
I will make this homework due on Monday. But if we can finish a new topic on Friday's class, you may have 2 homeworks due on Monday. You know what I mean? So since we have one more example, so it was originally planned to do on Friday morning, before the class. Sorry, Friday before the class. But since we cannot finish all the example problems, so I will postpone it to Monday before the class.
Is the homework open?
I may forgot to assign the homework. I will do it now.
Okay.
But I already post the homework on Canvas in files.
Sorry, you said it would be due before Monday, due before Monday's class?
Yeah.
Professor, how's attendance tracked to make sure we get the extra credit?
TA will do that. They will check that if you are here for the entire 75 minutes, and if your video is on, and if your video show that you're actually taking the class, you're not doing something else, then TA will give you 1 point for each class. And in the end, if you have, let's say, 100% of attendance, you get 3 points. You have 50% of attendance, you get 1.5.
Perfect, thank you.
When we're doing the homework, do you have any rules on like significant figures or anything?
That's fine. 3.
3,
4.
okay.
Yeah, it doesn't matter.
Okay, thank you.
And also in statics, they're really particular about how we formatted our homework. Do you have any formatting, any style you want us to format it in, or just answer the questions?
No, it's not just answer questions. You do need to write the steps. I don't really care about formatting. You can use any formatting you want. The thing that you want to make sure that the steps you write there is very clear for TA to grade. And we do the grading by the steps. So we do partial credit. If you show the correct step, we will give the points of corresponding to that steps. So I really don't care about formatting. We care about the content you write there. Make sure that it's clear for the TA to read.
Okay, thank you.
Make sure you put enough information. It's not just put the final number and say, okay, the final number is here. No, we grade by the steps.
So if we just have a free body diagram and the equilibrium equations and the answer, that's all we need.
Similar as what I'm doing here. You need to show, let's say you need to show this one, you need to show this equation and everything. It's not, if you only put this number here, I mean, we cannot grade something like this. You should do similar as what I'm doing here in the class.
Thank you.
You're welcome. Any other question? For example 1, why MC is considered negative when CB, for example 1, MC is clockwise. So when we put everything in the equilibrium equation, everything follow the coordinates. So follow the coordinates, this becomes a clockwise moment. That's why we have negative sign. For the global coordinates, this is a positive moment. This is negative moment. Yes, attendance will start from Monday next week because right now it's still the add drop deadline. Some students still, I don't know, they may drop, they may add. So we'll take the attendance start from Monday. Yes, you need to have the camera on for the whole time. It's an internal moment still considered as it's an internal moment for which point? Internal moment on this negative surface, this is considered as a positive moment. But when we put this moment in the equilibrium equation, everything follow the coordinates, which means that now this clockwise should be a negative moment. Makes sense or not? We are doing in this way because we want to make sure that, let's say, if we take this section, this is a positive internal moment. And if we take this section, this is a positive internal moment. In the end, no matter we take the left side or right side, we get the same answer. That's the whole point why we have the sign convention of internal force, why in the equilibrium equation we always follow the coordinates, because in the end it should be the same answer no matter we take the left side for the calculation or right side calculation. The moment at that point should be the same. It has to do the fact that its tension right hand will give you the counterclockwise moment at the side. It's tension. Okay, I don't understand. Right, what tension here give you a moment? If it's tension, it passes through the point you are calculating, since there's no moment. Actual force does not generate moment. If you choose C or B or D, right? Because the actual force pass through the C point, B point, and D point. There's no moment generated by the actual force.
I had a question about the homework real quick. I was just looking at it and it asks to find like internal forces at like D and E, but there's like 4 locations, like there's like F and everything else. We can just ignore those when we're calculating the other ones.
Yeah, ignore the
Okay.
rest. Yeah.
All right, thank you.
You're welcome. Any other question? So if no question, I will change to the office hour Zoom link, and you can, if you have any question, you can come to my office hour. Yeah. Okay. Thank you.
Thank you.
Have a great day.
Bye. Thank you.